What is a Peltier cooler? What is the scientific explanation? What are Peltier coolers doing on Mars? What is its connection with radioactivity? All and more in this video.
A long time ago, I bought a Peltier cooler for a project. I gave up on that project for various reasons. But while I was working on computer the other day, I found some video recordings about this project. At that time, I was only sharing the project I made on this channel. That's why I didn't post anything. But over time, the channel became a little more general. So, I thought I'd use those images for a video giving information about Peltier coolers. At that time, I bought this Peltier cooler from Turkey for 42 Turkish lira, but it was 2021. Currently, this same cooler is sold for around 155 Turkish liras in Turkey. So, why did I give up on that project? To answer, we need to understand Peltier coolers a little better. To understand Peltier coolers, we must first know about thermoelectric. Because the official name of the Peltier cooler we use today is actually thermoelectric cooler. Thermoelectric, as its name suggests, is the branch of the science that studies the relationship between heat and electricity. The father of this science is German physicist Johann Seebeck. In 1821, Seebeck connected two different metal plates and heated one of them. He saw that with the temperature difference between two metals, the metals moved a nearby magnet. In other words, the temperature difference between the metals created an electric current, and this current created a magnetic field. In 1834, Charles Peltier, who gave his name to the piece we have, discovered that the opposite effect observed by Seebeck also existed. In other words, just as the temperature difference between metals can produce electricity, it has also been revealed that the electricity given to metals creates a temperature difference between these two metals. When you connected one direction of the electric current to one metal and the opposite direction to the other, one of the metals would heat up and the other would cool down. These scientific studies led to the semiconductor-based Peltier coolers that we see today. The main reason why I gave up the own project was actually the main problem with Peltier coolers. Seebeck and Peltier explained the effects they found with very beautiful formulas. I don't want to drown you in mathematics, so I will show it in practice. Please follow on the screen. Let's start with the Seebeck effect first. I heat the Peltier cooler in my hand with a lighter. As you can see, the sudden heating of one side creates a temperature difference between the two surfaces. This quickly provides us with electricity of 1.3 volts. The highest voltage we can get from these ceramic coated coolers is close to this. If we can create a temperature difference of around 40 degrees between two surfaces, the voltage we can get is 1.5 volts. This is the highest level of efficiency obtained from devices to date. Of course, in order to produce these temperature differences without damaging the material, it is necessary to heat one of the surfaces while cooling the other. It is important that we cool a surface, so that we can heat the other surface at temperatures that will not harm it. Likewise, we have some restrictions on efficiency in the method we call the Peltier effect, which creates a temperature difference between these materials through electricity. As we said, to get the best efficiency from Peltier cooler, you need to control the temperature difference between the surfaces. If one side gets too hot, the cold side won't be able to cool any further. In order to control this temperature difference in the project, I tried to distribute the heat of the hot side with the help of a fan. Please follow on the screen. Initially, both ceramic surfaces were around 25 degrees, but then applied 12 volt current. The temperature difference between the surfaces increased rapidly. While the cold side dropped to 10 degrees, the hot side approached the 50 degrees. In fact, this shows the highest efficiency you can get from this device. You can keep the temperature difference between the two surfaces around 40 degrees. So, if you allow this hot side to be 50 degrees, you can reduce the cold side to 10 degrees at most. So, if you want to benefit from these devices in the field of cooling, you need to insulate the two sides thoroughly from each other and cool the hot side as much as possible. For example, if you want a temperature of 0 degrees, you should not let the hot surface exceed 40 degrees. You should create the cooling system of the hot side accordingly. In other words, while you have to spend energy to run the Peltier cooler itself, you also have to spend energy to cool the cooler again. So, for this 10 degree gain, what is the energy cost of this cooling without spending any extra energy on cooling the cooler itself? Here is the reason why I gave up on the project. I was working on mobile project at that time. During this test, the amperage drawn by my device from 12 volt power supply is around 2.25. So, even in this simple form, we have a mechanism consumes 25 watts of power. To get this to lower temperatures, I would need at least 30 or 35 watts of power. This is a power level that will drain even the largest power banks sold for phones in the market in 1 hour. So it would either be used for a very limited time, or I would have to drive around with a car battery 50 times the size of the device for a teeny cooling device. For my project, I didn't find this Peltier cooler very efficient. That is why I gave up on the project then. So, are these devices useless? Because of the method I mentioned, they are not widely used, but they are not unusable at all. If your power requirement is not very high, and you already have an environment where you can create a temperature difference, the inefficiency of this method disappears. They are used in very special projects. For example, the thermoelectric effect is used to produce energy in NASA's Curiosity space robot, which was sent to explore Mars. A radioactive material inside the robot constantly decays and produces heat on its own. The surface of Mars is already cold. In this case, a temperature difference that is efficient and does not require an extra energy source emerges. Apart from this, although there are innovative usage areas, it is still not a very common usage area. After all, you cannot travel around with radioactive material everywhere, or you cannot find a source that is too cold or too hot on its own anywhere. Under Earth conditions, you generally need serious energy to control the temperature. Today, I wanted to use of the images of a cancelled project of mine and give you information about the Peltier effect and the use of this effect. I hope it was a useful video for you. If you enjoyed it, don't forget to like the video and subscribe to the channel. See you in the next video.